morning, everybody. Thank you for joining us today, and welcome to our monthly webinar series. Today's topic is Power Quality, a Detailed Understanding of Harmonics. My name is Sarah Bauman, and I'm the Marketing Programs Manager for Megger NAFTA. And I'm stepping in for Jamie Smith, our Digital Marketing Specialist, as he's on his way home from the IEEE TMD Conference in Denver. I'll be acting as your moderator for today's presentation, and I'll support you on any technical issues or questions for our presenter. On the right side of your screen, you'll see a panel that looks similar to this one. Excuse me. You can submit questions to me at any time throughout the presentation, not just now, but in the middle, at the end, whatever the case may be. And by typing in the box highlighted in red, and I'll read their questions at the end if time permits. Unfortunately, we do get a lot of questions, so we'll try to get to them as time permits. You are eligible to receive one NETA CPD and one PDH or 0.1 CEU for attending. Excuse me. You'll receive this in an email within 2 business days after the webinar. The email will also include a copy of this presentation, excuse me, and a link to the video recording of the webinar. And we will have that on our website as well, so you can share that with your colleagues if you wanted to. Excuse me. Remember, you can ask questions at any time, and we will go over them at the end of the webinar in the Q&A session. Our presenter today is Sanket Bolar. He's our applications engineer in the substation area. And also to assist with the Q&A session, we've got a panelist, Mr. Andy Fagel. He's a product manager with Megger. Okay, we're going to go ahead and get started. Thank you for joining us today, Sanket.
Thank you, Sarah. All right, guys, so let's begin with the presentation. So today's agenda, the points that we are going to cover during today's presentation is we are going to start off with the theory. So we're going to do a little bit of theory on harmonics, then we're going to move into the sources of harmonics, how are harmonics generated. We're going to look at some of the sources. Then we're going to get into the third section, which is current and voltage. What's current harmonics and what's voltage harmonics. We're going to look at how harmonics are measured. We're going to see what are harmonic indices, THD, TDD, what does that mean? Harmonic power, we are going to look at harmonic power flows. We're going to talk a little bit about power factor. Then we're going to look at what effects do harmonics have, why are harmonics so important for us, harmonic evaluation procedure, harmonic mitigation techniques, so how to control harmonics. So these are the points that we'll be covering during the presentation, and let's start off with the first section. So theory, what are harmonics? So if you see a clean waveform, a pure sinusoidal wave, that waveform will consist only of the fundamental frequency component. What do you mean by fundamental frequency? Fundamental frequency is the system frequency. So in a 60 Hertz system, the fundamental frequency is 60 Hertz. In a 50 Hertz system, it's 50 Hertz. What do you mean by that? Well, if you take a wave and that's a complete cycle. If you say it's a 60 Hertz wave, it means that it completes that 60 cycles like those in 1 second. So that's what you mean by frequency. So if you take a clean waveform, it will only have the fundamental frequency component, but in real life, there is always some amount of distortion present in the waveform, voltage or current. And that's because there are other frequency components present in the waveform apart from the fundamental frequency component. Now, those frequency components produce distortion. And the frequency components which have frequencies which are integer multiples of the fundamental frequency are called harmonics. So let's take a simple example to see what distortion looks like. Here we have a clean waveform which just has the fundamental frequency component. So you can see that it's a clean sinusoid. If you look at the y-axis, you can see that the peak of the wave corresponds to a magnitude of 1, and on the time is in milliseconds, this is one cycle of the waveform, and it takes 16.66 milliseconds to complete the cycle. So by looking at the time, I can tell that it's a 60 hertz wave. Now let's take another wave. This you can, if you look at the x-axis, it's the same. It's 16.66 milliseconds, but you see that there are 3 cycles in the waveform. So 3 cycles in the same amount of time, and the magnitude, if you look at the y-axis, you will see that the peak corresponds to a value of 0.2. So the magnitude is 20% of the fundamental wave. Now let's take a third waveform. Again, the time is the same, but this time we have 5 cycles on the screen, and the magnitude is again 0.2. So it's 20% of the fundamental. Now, if you take these 3 waveforms with different frequencies and you mix them up together, what you get is this. So this is a very simple representation of how the waveform gets distorted because of the presence of different frequency components. Okay, so in the previous slide, you saw that on the screen it said 20% third harmonic, 20% fifth harmonic. What did we mean by that? Third, fifth, these numbers are called the harmonic orders. And harmonic order is the ratio of the frequency of the harmonic to the fundamental frequency. So a third harmonic means that the frequency of the harmonic is 3 times the fundamental frequency. So the frequency of the wave would be 180 hertz. For a fifth harmonic, it would be 5 times the fundamental frequency. So the frequency of the wave would be 5 times 60, which is 300 hertz. Frequencies, the harmonics with odd orders are called odd harmonics, and harmonics with even orders are called even harmonics. So third, fifth, seventh, ninth, 11th, those are odd harmonics. Second, fourth, sixth, eighth, 10th, so on and so forth are the even harmonics. Harmonics can also be classified in terms of their phase sequence. So what's phase sequence? Phase sequence refers to the phase relationship between the 3 phases in a 3-phase system. So if you look at the vector diagrams there, you'll see that the first one is for a positive sequence system. In a positive sequence system, B lags behind A by 120 degrees. C lags behind B by 120 degrees. So if you go from A to B to C, you move in a clockwise direction on the vector diagram. Now the same vector diagram, if you had a negative sequence system, it's quite the opposite. So B would lead A by 120 degrees. C would lead B by 120 degrees. So if you go from A to B to C, you would move in the counterclockwise direction. In a zero sequence system, there is no phase difference between the 3 phases. All 3 phases are in phase with each other, which is represented by the 3 arrows coincident with each other. Now that's the phase sequence, the phase relationships in the 3 phases on the 3 types of systems. Now, based on their phase relationships, the harmonics can be classified under these 3 categories. So the fundamental, 4th, 7th, 10th, 13th, so on and so forth, these harmonic orders fall under positive sequence. 2nd, 5th, 8th, 11th, 14th, these are all negative sequence harmonics. And the multiples of the 3rd harmonic, 3rd, 6th, 9th, 12th, these harmonics fall under the zero sequence harmonics. Triple N harmonics. So what are triple N harmonics? Triple N harmonics are odd multiples of the 3rd harmonic. So 3rd, 9th, 15th. Remember, we spoke about zero sequence harmonics in the previous slide. Triple N harmonics are zero sequence harmonics, but all zero sequence harmonics are not triple N harmonics. So triple N harmonics, being zero sequence, add at the neutral of a Y-connected system. So because they are zero sequence harmonics, on a 3-phase system, the currents flowing through the A, B, and C phases do not have any phase angle difference between them. They are coherent, in phase with each other. And so when they converge at the neutral, they add up, and that results in the total amount of current flowing through the neutral conductor. The neutral is grounded. So the effect of that is if there is a lot of zero sequence harmonics in the system, all of that zero sequence harmonics will flow through the neutral, and if the neutral is not sufficiently sized, then there will be overheating of the neutral conductor. Also, these zero sequence harmonics or triple N harmonics can be trapped in the delta winding of a transformer. So one of the main applications of the delta winding of a transformer is to provide a circulating path for zero sequence currents. So if there is a fault, or if zero sequence currents flows in the system of when it comes across a Y delta system, a grounded Y and a delta system, the zero sequence currents will flow into the Y winding and down to the neutral. But on the other side of the transformer, they'll circulate in the delta winding and the currents won't propagate through the system. Okay, so that was a little bit about the theory of harmonics. We covered a few terms there. Now let's move into the next section of the presentation, which is sources of harmonics. So how are harmonics generated? Why all of a sudden do we have this problem? Harmonics, the problem of harmonics is very recent. Excuse me. And that's because of increasing use of non-linear loads or loads which draw current for only a portion of the voltage waveform. Transformers have been around for a long time, for longer than electronic power converters, let's say. So harmonics have been around. The problem of harmonics has been around for a longer time, but it wasn't so prominent earlier before the advent of electronic power converters or electronics. So harmonics arise out of non-linear loads. What are non-linear loads and what are linear loads? A linear load is a load whose impedance or resistance doesn't change with the change in voltage. So take a resistor of 1 ohm. If you apply 5 volts across it, you'll get 5 amps. If you apply 10 volts across it, you'll get 10 amps. Non-linear loads, on the other hand, the impedance changes with voltage. An example is a transformer on no load. So if you take a transformer with its secondary open, if you apply voltage across it, and if you continue increasing the current, initially there will be the relationship between the voltage and the current that it draws, the exciting current. The relationship between the voltage and the current will be linear at low levels of excitation. But as you increase the voltage, slowly it will start becoming non-linear. So the rate of change of current will start increasing as compared with the rate of change of voltage. And as that happens, you notice that the current becomes more distorted. And that's because of the saturation characteristics of the core. We can highlight this using a CT. Let's look at the CT saturation curve. So a saturation curve of CT is what it looks like. On the y-axis, you have the voltage that's applied across the secondary winding of the CT. On the x-axis, you have the excitation current, the current that the CT winding draws. You can see that there's a point marked as an asterisk on the graph, and that's your saturation voltage. It's about 180 volts, which tells me that the CT is a C200 CT. Anyway, so now we're going to take 2 points on the curve at different voltages, one at 50 volts, one at 30 volts, 130 volts, and let's observe the waveforms on those 2 points. On the left, you have the waveform at 50 volts. The current is the one in purple. If you look at the waveform, it's pretty clean. It's sinusoidal. And if you look at the current waveform on the right at 130 volts, you'll see there's quite a bit of distortion on the current waveform. Switch mode power supplies. So these are one of the most common sources of harmonics, because switch mode power supplies are used by a lot of devices, computers, printers, copiers, that you find very common. Switch mode power supplies draw current for a portion of the voltage waveform. Switch mode power supplies are essentially rectifiers. So what happens is the AC that you get out of the wall outlet, that's converted into DC. DC is then converted back into high frequency AC, and that's again converted back into DC to give a smooth ripple-free DC. Now, because switch mode power supplies have rectifier circuits in them, there is a capacitor on the output side of the rectifier circuit which charges and discharges every cycle, and it draws a short amount of current when it charges, and that corresponds to the peak of the voltage waveform. So let's take a simple simulation from a full wave rectifier circuit. Now, if you look at this, there are two waveforms here. The waveform on the top, the one in blue is the input voltage, and the one in yellow is the capacitor voltage. You see that initially it draws a high amount of current. Now, if you look at this input current, it draws a high amount of current in the first cycle, and then the current that's drawn by the capacitor decreases slowly as the voltage across the capacitor increases. At a certain point, it seems that the voltage across the capacitor is stable, but if you look closely, you'll see that it's not a straight line. You'll see that it charges up by a little bit and discharges until the next cycle, and the process is repeated every cycle. So you get this kind of a waveform from a rectifier circuit. You'll see that the current is alternating pulses. Basically, it's not a sinusoidal wave. It has pulses on each half cycle, and the pulses correspond to the peak of the voltage waveform. So this is a simulation. Now let's look at a real waveform from a computer. You can see that there is a lot of similarity. You have these pulses, these current pulses, which are really sharp, and that's because of the capacitor on in the switch mode power supply. On the right, you have the harmonic spectrum. Harmonic spectrum tells you exactly what the magnitude of each harmonic order is with respect to the fundamental. So the first bar graph that you see is the fundamental, and that is at 100%, and all the harmonics are compared with respect to the fundamental. You can see that the harmonic spectrum, this harmonic spectrum has mainly odd harmonics. So there is third, there's fifth, there is seventh, ninth, 11th, and the magnitude of the harmonics decreases as the order increases. So that's a typical harmonic spectrum that you get from a computer. You can see that the current, even though the harmonics, the harmonic content is high, you can see that the current that's drawn by the computer is small. The peak corresponds to a value of 2 amps. But if that's one computer, imagine a building which has 50 to 100 working computers in it, and imagine the amount of third harmonics, or the amount of zero sequence harmonics flowing in the neutral of a transformer that's feeding that building. Another example of harmonic sources is fluorescent lighting. Fluorescent lights are discharge lamps. So the way a fluorescent light works is there's gas inside the lamp, and an initial high voltage is required to kind of cause a discharge. And when the discharge happens, when the light is established and there's current flow, the current increases initially. So to limit the current, you need a device. So the device that's used along with fluorescent lights is the ballast. As you can see, the type of ballast that's used with fluorescent lights has an influence on the amount of distortion in the current waveform. There are two types of ballast: magnetic ballast and electronic ballast. Magnetic ballasts are simple. They have an iron core transformer, capacitor. Electronic ballasts employ a switch mode power supply circuit. So there's switching involved, and you can see that there is much more distortion when electronic ballasts are used. Both types of ballasts have their own advantages and disadvantages, and that's why people use either of them. The next example of a harmonic source is drives. Drives are used commonly in industrial facilities for various applications. There are AC drives, there are DC drives. AC drives convert AC to DC and then convert it back to AC, possibly of a different frequency. In AC drives, you have different types of drives. There are two types mainly. There's voltage source inverters, there's current source inverters. Voltage source inverters have a capacitor in the DC link, and current source inverters have an inductor in the DC link. You can see that the curves on this particular waveform, you can see that the current pulses are quite similar to what we got with a computer, and that's because it's essentially a three-phase version of a switch mode power supply. You can see that the pulses are sharp, and that's because there's no inductor in the circuit. But for current source inverters, the pulses won't be this sharp, it will be rounded out. That's because of the presence of an inductor in the DC link. On the right, you have again the harmonic spectrum. If you look closely, you'll see that it has a 5th and 7th harmonic content. It has 11th and 13th harmonic content. And the harmonic spectrum depends on the pulse configuration of the drive. So a 6-pulse drive will have 6 plus minus 1 order harmonics. It'll have 6 times 2 plus minus 1 order harmonics, and that's what you see on the harmonic spectrum. So just by looking at the harmonic spectrum, I can tell that this is a 6-pulse drive. Okay, so now that we have seen a few different types of harmonic sources, let's go into the next section of the presentation, which is current and voltage harmonics. So what are current harmonics? What are voltage harmonics? Current harmonics are what we saw so far. So whatever current comes out of a non-linear load or is drawn by the load, that's the current. That's the distorted current with the current harmonics. Now, when that distorted current flows through the system impedance, it gives rise to voltage distortion. Okay, so you can say that voltage harmonics are caused by current harmonics. So the current distortion depends on the load, solely depends on the load, but the voltage distortion depends on the current as well as the system impedance through which the current passes. So this is a simple representation of the load flowing through the system and causing distortion at the load bus. There was a short section. Let's move on to the next one, which is on harmonics measurement techniques. So how are harmonics measured? The standard that deals with harmonics measurement is IC 61000-4-7. The measurement interval specified in the standard is 200 milliseconds. That corresponds to 10 cycles or 12 cycles, depending on whether the system is 50 Hz or 60 Hz. The 200 millisecond values can then be aggregated over longer intervals of time. So 3 seconds, 10 minutes, or 2 hours. And that's for Class A instruments. There are different types of instruments specified in the standard, different types of requirements for those different types of instruments. So Class A, Class B, and Class Class S, I'm sorry. Class A has the most stringent requirements, and this is this is what the intervals are that are specified for Class A instruments. It also says that at least up to the 50th order harmonics need to be measured. So how are harmonics measured? There are two domains essentially. There's time domain and there's frequency domain. So the waveforms that we saw so far during the presentation, all the waveforms were in the time domain. And the harmonic spectrum that you saw, that's what you get after breaking the waveform up and into the different frequency components and essentially converting it into frequency domain. So how is the conversion done from time domain to frequency domain? It's done by a technique called DFT, discrete Fourier transform, or a faster version of it called fast Fourier transform. when you analyze a waveform and do DFT, FFT on it, you get the frequency spectrum of the waveform, and you essentially get different frequency components over the wide range of frequencies. Now, how do you come up with harmonics from this? What you get is essentially those red graphs that you see. Each red bar corresponds to a 5 hertz bin. So let's take 180 hertz for example. The frequency of 180 hertz is at the center band, is at the center of a 5 hertz bin. There is a 5 hertz bin to the right of it. There's a 5 hertz bin to the left of it. So if you take those three 5 hertz 5 hertz bins around 180 hertz, you get a single 15 hertz band, and all the frequency components which feature in this 15 hertz band. So 180 plus 7.5, 180 minus 7.5, all those frequency components would be grouped under the third harmonic. Similarly, if we go to the second or harmonic frequency, 120 hertz, take the 15 hertz band around 120 hertz, so plus minus 7.5 hertz. All the frequency components which show up in this bin are in this band are grouped together under second harmonic. Okay, so the next section we're going to look at harmonic indices. So you might have heard the terms THD, TDD. What do you mean by THD? THD is total harmonic distortion. It's a single parameter used to quantify the presence of harmonics in the system. It is obtained by using all the individual harmonic components that you get and essentially using the ratio of the individual harmonics to the fundamental. So you can see the formula there. And as per the European standard EN 50160, the acceptable limit for voltage THD is 8%. Now, can this term be used for current? We'll see that later. But before we do that, let's look at the chart for total harmonic distortion. This is what a chart looks like. This is from a week-long recording, maybe about 8 days. If you see closely, you will see that there is a bit of a pattern here. It repeats itself after every cycle actually corresponds to a day. So why is that? Because THD corresponds to the load of the plant, and that's why it's essential that when you do harmonics measurement at a facility, you need to keep the recorder in there for at least a week to get the full picture. Okay, so voltage and current fluctuation wise, there's not much fluctuation in voltage. Voltage stays pretty much constant, close to the nominal value. But the current can change drastically over a short span of time based on the load. So if the load could draw 500 amps 1 second, the next second the load could drop to 50 amps. So there's a lot of changes in current. So let's take a constant harmonic current of 1 amp in the system. If the fundamental is 10 amps, the harmonic percentage wise, that harmonic current is 1 divided by 10, 10%. If the fundamental goes up to 100 amps, the same harmonic current becomes 1%. Right? So if we use the same principle that we use for voltage and calculate the THD, taking the fundamental into consideration, we're going to have, we could get the wrong picture. So THD is not the ideal term to use for current harmonics analysis. That's why we go with a term called TDD, total demand distortion. For TDD, the fundamental is taken as the max peak current recorded over the demand interval is used as the fundamental. So if you are recording with 15-minute demand intervals, the current that's the peak value that's recorded over that 15-minute interval would be the fundamental for TDD calculation in that 15-minute interval. So this is the comparison of a THD chart and a TDD chart. On top you have the THD chart, in the bottom you have the TDD chart for the same recording. If you look at the pattern, you will see that they are pretty similar to each other. They follow the same pattern. But if you look at the values on the y-axis, you'll see a drastic difference here. On the THD, it ranges from 7.8 to 14%. For the TDD, however, the values are pretty much within 1%. So the next section is on harmonic powers. Power is measured by looking at the true RMS values of voltage and current. Harmonic powers, if you take individual harmonic powers, the flows, the direction of the flows differs from harmonic to harmonic. So it's not essentially the same as the fundamental power. So you get the direction of the power flow by looking at the phase relationship of the harmonics with the fundamental. If the phase angle difference lies in this range, so between 90 to 270 on the positive side, then the direction is from source to load. If the phase angle difference is in the negative quadrant, so if it's in this range, then the direction is from the load to the source. This is a power waveform, and on the right you can see the harmonics, individual harmonic contents in the power waveform. Here you have a column for phase angle, and here you have a column for direction. Direction, it says either S or L, and that's determined from the phase angle difference. You can see the fundamental phase angle is 0, and all the other angles are looked at with respect to the fundamental. If the direction is from source to load, then S is given in the table. If the direction is from the load to source, then the letter L appears in the table. There are two types of power factor values mentioned in the power quality field. We'll look at what those mean. Displacement power factor, true power factor. Displacement power factor is the cosine of the phase angle between the voltage and current. It depends only on the fundamental component. True power factor is the ratio of the active power to the apparent power. In a harmonic free system, you're not going to get difference between the displacement power factor and true power factor. So both of them are essentially going to be the same. The presence of harmonics, however, creates a difference. It causes the RMS values of the voltage and current to go up. So you're going to have higher RMS values for voltage and current, which is going to result in a higher kVA, which is going to again cause the true power factor value to go down. There's going to be a bit of a difference between the true power factor and displacement power factor if there are harmonics in the system. A classic example of this is again a drive, variable frequency drive. Now this is the demand report from variable frequency drive. If you look at the displacement power factor and true power factor, you'll see that there's a bit of a difference there. The displacement power factor is pretty close to unity. True power factor is lesser, it's around 0.86. Let's look a little further, and let's pull up the phase angle information. If you look at the phase angle difference between the voltage and current on the A phase, for example, we see that there's a phase angle difference of 10 degrees. The displacement power factor is the cosine of 10 degrees, which is pretty close to unity, 0.98, 0.99. But if you look at the true power is determined, the true power factor is determined from the ratio of the real power to the apparent power. and that's how you get the value of 0.86. This is what we are familiar with. This is for a harmonics-free system. So the relationship between apparent power S, real power P, and reactive power Q. But if you have harmonics in the system, there is an additional term D in the equation, and this is what the relationship becomes. Effects of harmonics. So what effects do harmonics have on the system? We already spoke a little bit about how zero sequence harmonics can cause overheating of the neutral. Harmonics can also cause increased copper losses or I square R losses. Harmonics are essentially currents, so they add to the heating effect that happens when current flows through a conductor. Harmonics can also cause eddy current losses. So what are eddy current losses? When current flows in the vicinity of a metal part, the field of the current sets up local circuits in the metal part. It induces EMFs, and these local induced EMFs set up local circulating currents in the metal part. Those currents are called eddy currents, and those eddy currents cause eddy current losses. Besides that, there are different core structures. The bigger transformers usually have a 5-legged core. So you have the 3 legs of the core on which the windings are present, and there are 2 auxiliary limbs. On smaller transformers, however, the cores are 3-legged. So when you have zero sequence currents in the system, there's going to be zero sequence fluxes in the core, and those zero sequence fluxes will need a return path. In a 3-legged core, the only return path is to escape through the metal parts of the transformer. So whatever is metal inside the transformer, apart from the core, all of those metal parts are not meant to be there to handle flux flow. So obviously there's going to be a lot of heating, there's going to be deterioration because of that. So zero sequence fluxes can cause a lot of problems in 3-legged core transformers. So because of whatever harmonics do to a transformer, there is a standard that deals with using a transformer on a non-sinusoidal load. The standard is called C57.110, and there's a term called K factor which is mentioned to indicate to enable the sizing of a transformer with respect to the load that's being used. So based on the harmonic content of the load, we arrive at a factor called K factor. Formula is given on the slide. You can see that the formula includes 3 terms: IH, IR, and H. IH is the individual harmonic current. IR is the total current or the fundamental current. H is the harmonic order. So you can see that the harmonic order shows up in the formula, and that's because the eddy current losses that are caused by harmonics depend on that are proportional to the square of the frequency of the currents. That's the reason you have the H square there. Now, if the K factor that's calculated from the load is, let's say, 2, then the transformer that's going to handle that load needs to be a K4 transformer. And I'm just giving you an example. The K rating of the transformer needs to be higher than the K factor that's obtained on the load. Effects of harmonics on motor. Harmonic voltage is going to result in harmonic fluxes which rotate at a frequency different than the rotor frequency, which rotates at close to the fundamental frequency. So the frequency difference is going to the interaction between the flux and the conductor is going to result in induced currents. These currents are going to cause heating and losses. Besides that, the interaction between the currents and the field results in a torque called pulsating torque, That's going to cause oscillations on the shaft. Now, if the frequency of the pulsations matches with the natural frequency of the shaft, then that can result in a mechanical resonance that can basically amplify the effect that occur due to these oscillations, and can also result in damage to the shaft. So what is resonance? We're talking about electrical resonance here. What is it? So in a circuit, you have a resistance, you have an inductance, you have a capacitance. If the inductive reactance matches with the capacitive reactance, inductance and capacitance essentially have opposing effects on a circuit. If the inductive reactance is exactly equal to the capacitive reactance, then the resultant reactance of the circuit becomes zero. So the only obstruction that you have in the circuit is the resistance. So when that happens, what you have is an easy path for currents to flow. Resonance can occur in two ways, series and parallel. If the inductor and the capacitor are in series, then it's series resonance. If the inductor and the capacitance are in parallel, then it's parallel resonance. So how does this show up on how does this relate to harmonics? I told you that the resonance condition is achieved when the inductive reactance is equal to the capacitive reactance. If you simplify the equation a bit, you get the role of frequency in the circuit. So the reactance is frequency dependent. So apart from L and C, if F shows up in the equation, and if the L and C on the system are such that resonance, that equation is met at a particular harmonic frequency, then it will result in a large amount of harmonic currents of that particular frequency flowing in the resonance circuit, basically amplifying the voltage distortion that would have normally occurred if there was no resonance. These are two pictures highlighting the effect or how parallel or series resonance can happen. On the left, you have a harmonic source. There's a capacitor bank in parallel with it. There is a transformer here. There's source impedance. So the harmonic source essentially sees it as a parallel resonance circuit. You have the C in parallel with the L. On the right, you have a series resonance example. You have all these harmonic sources, and all these harmonic sources see this particular portion as a series LC circuit. So you have the transformer in series with the capacitor bank, and that's series LC circuit. If the frequency of these harmonics is such that it meets the resonance equation, then there's going to be a high amount of current flow through this branch. Now let's come to this section on harmonics evaluation. Harmonics evaluation, we spoke a little bit about current and voltage harmonics. Current harmonics depends wholly on the load. So it's the customer that's responsible for making sure that the current harmonics are within limits. When these current harmonics, when the distorted current flows through the system impedance, it's going to result in voltage distortion. So it's essentially the utility's responsibility to make sure that the voltage harmonics are within limit, provided the current harmonics are within limit. Evaluation is carried out at the point of common coupling. Point of common coupling is a point at which a utility serves multiple customers. And as I said, the duration should be at least 1 week to make sure that the plant cycle is covered. So this is a simple diagram. You have the utility, you have electricity coming in. There's a transformer. There's a bus feeding two customers. The point of common coupling here would be this particular point. So you can hook up the recorder on the secondary of the transformer or on the primary of the transformer, You have to understand though that if it's a delta Y transformer and if you do the measurements on the secondary, you're going to see the zero sequence currents. On the primary side of the transformer though, on the delta side, you won't see those zero sequence currents, as the zero sequence currents are trapped in the delta winding of the transformer. Harmonic mitigation. So what are the different approaches to control harmonics? One is you can reduce the harmonics on the load itself, which is kind of limited. I mean, most of the devices are designed to particular specifications. Take an overexcited transformer, for example. You can bring the excitation level down, and that would reduce the distortion in the current. You can use filters, so shunt or series filters. Shunt filters act as a shunt. They bypass the harmonics that they are intended to bypass. Series filters suppress the harmonics. Changing system response characteristics. So, for example, to avoid resonance, you can change the L and C of the system to make sure that the resonance doesn't occur at a particular frequency F. So that brings me to the end of my presentation. Before I wrap up, I would like to go a little bit over what we offer in the field of power quality. What we have is the MPQ 2000, which is a three-phase power quality analyzer. It measures harmonics, yes, but it does a lot of things apart from that. It's a Class A measurement device. Remember, I spoke a little bit about the different classes specified in the IEC standard. So it's a Class A measurement device. It has auto CT identification, configuration verification. These features are intended to make sure that there is minimal operator error. It can be frustrating if the user places the recorder at a particular location, records for 1 week, and then finds out at the end that all this information was wrongly recorded. There was some mistake during the recording. So to avoid that, we have auto CT identification, which tells you that there is a mismatch. If there's a mismatch between the CT ratio that's entered and the ratio that's programmed on the recorder, you get a mismatch message. Configuration verification tells you whether you have hooked up in the right manner. If you have a delta, if you program the recorder to record on a delta and you hook it up on a Y connected system, it will tell you that you're hooked up wrong. If you connect the CT backwards, it will tell you that the CT is hooked up backwards. It doesn't need a separate power outlet. It's part of the A phase of the system to which it's connected. All the test data is recorded on SD cards. The maximum memory that it supports is 32 gigs, so memory is not a limitation at all. It's very rugged and portable. It's IP54 rated with the lid closed. It also has onboard data analysis on it. So if you want to carry out statistical analysis of data on the recorder itself without having to download it to your computer, you can do that. You can create your own templates or follow the templates that are given on the recorder, that are provided on the recorder as per EN 50160. These are some screenshots from what the screen looks like. On the left, you have the unbalanced screen where it shows you the vector relationships between the three phases. On the right, you have the recording screen, so you can see the voltage and the current. The configuration verification message. If you make any mistake while making connections, it gives you a message when you start recording. On the right, you have the onboard data analysis screen. It's the reference that I use for this presentation. Thank you guys for listening in, and I'm gonna have Sarah take over.
Awesome. Thank you, Sanket. Great job. All right, that concludes the presentation portion of our webinar. We're going to get into our Q&A section. And again, on the right side of your screen, there's that Q&A box if you've got some questions. We've already had a ton of questions rolling in. Again, I just want to remind everyone that a copy of the presentation, along with a link to the video recording of the webinar, it will be emailed to everyone within about 2 business days after this concludes. So you'll be getting that in your inbox. We've got another recording coming up, or I'm sorry, not a recording, another webinar coming up next month. It's titled Test Data Management for NERC Compliance Reporting. It's going to be on May 18th at 10 a.m. with Mark Meyer. He's a product manager for PowerDB. Also, all of our previous webinars you can find on our website. Just go to megger.com, select your country, go to webinars, and you can find all the recordings there. Right now, I think we're just going to go ahead and jump on in. I'm going to kind of go between Andy and Sanket, so we'll kind of tag team both of you. The first question I'm going to toss to Andy. Let's see here. We've got a question from Jeff. He asks, is it true to state that if a transformer is oversized for its use, then you run a higher risk of harmonic issues?
No, actually, when you the harmonics are actually caused by nonlinear loads. So provided that you're not operating the transformer in saturation, the transformer isn't going to create any harmonic issues. The harmonics will be created by the nonlinear loads that are connected to it. So typically, when you get a K-rated transformer, which is K-factor derated, it's typically going to have oversized coils or oversized ground in it to help deal with the eddy currents that are caused by these nonlinear loads that are creating the heating issues that you see within the transformers.
Perfect. Sanket, I'm going to toss one your way. This comes from Prem. He's asking, how do we categorize 1, 4, 7, 10 are positive sequence harmonics and 2, 5, 8, and 11 are negative VE?
Okay. So that depends, like I said, that depends on the phase angle relationship. And the 4th order harmonics, let's take positive sequence harmonics, for example. The 4th order harmonics, 7th order harmonics, 10th order harmonics, they, it's basically a I could explain it to you in a mathematical equation. If you put the frequency in there instead of omega, if you have 4 omega, and if you look at the phase angle differences, it basically has the same phase angle relationship as the fundamental. So the relationship between the A, B, and C at 4 times the fundamental frequency ends up being the same as the positive sequence, or the same as fundamental. Similarly, for second harmonics, 5th, 8th, 11th, it ends up being negative sequence. So B for negative sequence, B. I mean, I said all this during the presentation. B leads A, and C leads B, but it depends on the frequency and the phase relationship between the A, B, and C phases.
Awesome, thank you. Andy, I've got one for you. This comes from Mohammed. He asks, which type of harmonics mostly occur in power systems, odd or even harmonics?
Odd is by far the more common, because when you look at your power supplies or nonlinear loads, they're going to be rectifying the AC into DC. Most equipment works off DC and has power supplies that rectify the power. These rectifiers will rectify the AC signal symmetrically, meaning the positive and negative of the AC both get rectified, which will always result in odd harmonics. When you start seeing high levels of even harmonics, that's typically an indication that there's a faulty rectifier somewhere, because now the signal is not being rectified symmetrically. So typically, high levels of even harmonics will be an indication that there's a bad piece of equipment somewhere on the system.
Okay, perfect. Sanket, the next one's for you. Unfortunately, I wasn't given a name on this, but they ask, can you please re-explain the harmonic grouping after DFT, FFT in frequency domain?
Okay, so what you're doing is you're basically breaking up the waveform into different frequency components, And when you do that, it depends on the sampling window, which basically in frequency it corresponds to 5 hertz. So you picture this: you divide the frequencies into 5 hertz bins. So by bins, what I mean is you have, let's say, 0 to 5, 1 to 0 to 5 hertz, 5 hertz to 10 hertz, 10 to 15 hertz, 15 to 20 hertz. So those are 5 hertz bins. So what you're doing is essentially breaking it up into different frequency components, and then whatever frequency components you're gonna have, like it's not always gonna be 180 hertz. There's gonna be 182 hertz. There's gonna be 183 hertz. There's gonna be 179 hertz. There's gonna be a component that's gonna have a frequency of 176 hertz. So you don't, for third harmonics, you don't just consider whatever has the frequency of 180 hertz. You also end up considering the frequency components which occur in the vicinity of 180 hertz. So I'm just giving you an example for third harmonic. When you get the frequency the frequency spectrum for the whole waveform, you look at the components that show up in the range of plus minus 7.5 hertz of 180 hertz. So when your recorder shows you third harmonic, if it's measuring as per the IC standard, it's not just showing you whatever the 180 hertz component is. It's not showing you exactly the 180 hertz component. It's measuring all the frequency components which show up in that band of 15 hertz, plus minus 7.5 hertz. So anything that's measured between 172.5 hertz to 187.5 hertz is classified as a third harmonic. That's what I meant by harmonic grouping.
Perfect. Andy, I've got another one I'm going to toss at you. This comes from Ahmed. He's asking, for TDD calculation, should I take the max current of my measuring interval of the rated current of my load?
Well, per the IEEE 519, when TDD is calculated, you're going to be using either a 15-minute or a 30-minute interval. For each of these intervals, you will calculate an average current, or you'll measure an average current for each of these intervals. And the reference you will use is the maximum average current that was recorded in your test interval. That's the reference to use for the TDD calculation.
Got it. The next one, Sanket, this one's for you. And it is from Mike. He's asking, was the 8% limit on harmonics referring to THD or TDD? It seems like it should be for TDD.
The 8% limit is given for voltage THD. So it's for voltage THD, not current. It's just referring to the voltage total harmonic distortion. As far as I know, I don't think there is any limit for THD or TDD on the current. I could be wrong. Maybe Andy could help out with this. But the 8% limit that I mentioned in the European standard, EN 50160, the limit is for voltage THD.
Yes, the 519 standard, there are some limits or recommended limits on TDD, but you have to calculate the short circuit current as well for your system. And I would recommend just looking at the 519 specification for those indices.
Okay. Andy, here's another one for you. This comes from Deepak. He's asking, can harmonics also lead to ferroresonances in transformers too?
Not typically. Ferroresonance is mainly going to occur in delta transformers, ungrounded transformers. This is a result typically of a load turning off rapidly. What ends up happening when you have long cable runs going to that transformer, and this applies to motors too, when you have long cable runs going to that transformer, those cables act as capacitors. They store a lot of charge in them. The longer the cable, the more charge you have stored. In the transformer is storing a large amount of energy in its magnetic field. So when you have a load that will turn off suddenly, it acts like a switch, and what can happen is that energy in the magnetic field will dump onto the cable capacitance. They'll add together and create a very large amount of voltage, which can be up to 5 times higher than what would usually be on that primary. So typically it's more load when the loads get low on ungrounded transformers. It's not typically due to actual harmonics.
Thank you so much. I think we've got time for about one more question. I'm so sorry, everybody. I know we've got a ton more questions we haven't even gotten to look at yet. I'm going to ask one more just for time's sake. Sanket, this one's going to go for you. It's from Ahmed, and he's asking, effective harmonics on transformer metal part is valid for any other load, even if it was single phase?
Yes, I think I understood the question fully, but if you mean that harmonics do the same thing if it's a single phase, then yes, it doesn't necessarily have to be 3 phase. If there's going to be harmonics in the current harmonics in the transformer, they're going to have the same effect, regardless of whether it's a single phase or a 3 phase.
Wonderful, thank you. All right, well, that's going to conclude our time for the Q&A session. As you leave and when you close your webinar window, a survey should pop up on the screen. We'd greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve our future webinars. And on the survey, there's a field where you can also request a demo or quote of any of our mega products. Also wanted to make you guys aware that we've got a great hands-on power quality and harmonics training course from AVO Training Institute. If you visit avotraining.com, you can view the upcoming schedule for all their courses. AVO's been doing training for over 50 years, and they've got some of the most knowledgeable and experienced instructors around, so I'd encourage you to take a look at that. Again, I apologize we weren't able to get to all the questions. We had some really, really good questions today. We'll try to get to those. As long as you entered in your email address whenever you registered, we should be able to get those questions answered for you. Thank you all for attending so much. Again, you can please remember to answer that survey, and we hope to see you at our next webinar. Everybody have a great and safe weekend. Thank you so much.